Hello, this lecture is going to be on stars. This is the first half of chapter 18. So we're going to discuss how stars form and how they change. So a star is a big ball of gas. It gives off light and heat because it's fusing. Our sun is an example of a star and is the closest star to us. A lot of people forget that our sun is in fact a star. Most stars are made up of hydrogen and helium. However, some stars can also contain sodium, calcium, and iron. Most stars are made up of hydrogen and helium because hydrogen has one proton, so that's the first element to form. Helium has two protons, so it's the second element to essentially form. In order to form helium, we go through fusion. So hydrogen atoms combine to form helium. This is a big process. I just want you to know that it takes essentially hydrogen forces together to form helium. Hydrogen has one proton, helium has two protons. Stars form from nebulas. Remember, a nebula is a cloud of dust and gas. This is an example of a nebula in this left-hand picture. Famous example is the Eagle Nebula. Gas has mass. Even though it's very small, anything that has mass has gravity. So the gravity of these little tiny particles over a very long time are going to slowly pull together. And when they pull together, they're going to start to spin. It's much like ice skaters. When ice skaters are on the ice and they're spinning and they pull their arms in, that's going to cause them to spin really fast. So as this cloud collapses and connects, it's going to start to spin. The center is going to be under a lot of gravity, intense pressure, so it's going to start to glow. Now, it's not fusing at this point. We're not forcing atoms together because there's not enough heat and pressure to do that, but there is enough heat in order to form a little bit of a glow. Because of the spinning motion, we have this disk forming. This disk is going to be a flat disk, and that's going to form the planets of the solar system. If you've ever noticed, our planets all form a straight line called the ecliptic, and all the planets revolve along that same plane. Now, a couple are angled a little bit, but for the most part, they're all in that same plane because they all formed in that disk, that same disk. And you're going to notice they all going to revolve around the sun in the same direction because they all, again, came from the same disk, revolving the same way. When we get this light forming, again, it's not from fusion, it's just from a little bit of a glow from the intense pressure. When we get a little bit of glow, that's going to be called a protostar. The root word proto means first, so it's the first form of light that we would get. And then the big ball in the center would become a star. Most stars are in a binary system. Bi means two. If you're riding a bicycle, you're riding a bike with two wheels. So a lot of stars they form near each other, so they will kind of capture each other's gravity and they will kind of wobble around each other. Typically, the center of mass is the point that they're going to revolve around, and that center of mass is going to be a little bit closer to the star that has the most mass. It's kind of like a seesaw. You're going to need to find that balance. Sometimes if somebody is bigger on the seesaw and somebody else is smaller, you got to move the seesaw back and forth on that, fulcrum in order to find the balance. Star clusters are groups of stars moving together in various patterns. We can have a globular or rounded cluster, which is an example here on the left. The one up here is also an example of a globular cluster. Or we can have open, or also known as loose arrangement. And the one here on the right is an open cluster. Now we can learn a lot from stars, even though we've never visited one, because we can use spectroscopy or spectroscopes. We can use an instrument that's going to separate the light that we get from the stars. A prism is an example of a spectroscope. It's going to take white light, which is all colors of the rainbow, put together to form white. When the light goes from a gas, which is low density, to a solid, which is a high density, my gas is going to slow down. My light is going to slow down. When it slows down, it's going to bend according to their wavelength. So the red has the longest wavelength, and blue or purple have the shortest wavelength. So you'll see a nice spread of the colors according to their wavelength. Now, a more common example of this would be a rainbow. That's where light goes from a gas in the atmosphere into water droplets in the atmosphere. And again, they slow down and they spread out the colors of the white light. Another example, we've seen this with seismographs. When we have an earthquake and the earthquake travels through the layers of the earth, the waves get bent as they hit the different densities of the layers of the earth. This spread of light is called a spectrum. So we'll use spectroscopes. So this is a spectroscope to look at a spectrum, which are the lines that you see. You look through the small end of the spectrum and you point this bigger window at the light source. The light's going to come through here and it'll separate the wavelengths on a scale. The scale is going to go from 400, about 350 or 400 nanometers to 700 or 750 nanometers. And that's the spectrum of our visible light. You'll notice blue short wavelengths. Notice the blue is down here around the 400 and 450 nanometers. Red has long wavelengths. It's around like 650 nanometers. Now, oftentimes on the scale, you'll just see 4, 5, 6, 7 because it's very small, so it's hard to write all of those big numbers in there. So, but they're all about in this hundreds of nanometers. Spectrums tell astronomers what composition are of stars. So we can look through these spectroscopes and we can figure out, I know that that star is 75% hydrogen. How cool is that? I mean, we don't even have to visit it. All I have to do is look at it and I can figure out what's in it and how much. When elements are heated, they produce light. Just like a light bulb, the filament in a light bulb heats up and that's going to produce the light. Same thing's happening with our stars. It's under a tremendous amount of pressure, and that's going to generate the heat that's going to cause them to light up. Every element has a different number of protons. If you look at the periodic table, every single element has a different number of protons. That is key because every element is going to produce a different wavelength then. Light's produced when electrons move up an energy level and then back down. When they move back down an energy level, they're going to release the extra energy off as light. The wavelength in which they release is going to depend on the distance that they travel. If they travel a big distance versus a small distance, they're going to give a different wavelength. And because we have different, every atom has a different number of protons and electrons, all of those distances are not going to be identical. They're all going to be different. So they're all going to give a different set of wavelengths. That's awesome. Okay, so what we did, scientists studied a whole bunch of elements in the lab, and every time they look at calcium, they get these exact 3 lines, no matter what. Every time they look at sodium, they get these exact 3 lines, and they have to be in that exact spot too. Iron and magnesium. So every element you look at is going to have a different spectrum. So we can use this as like a fingerprint. Every single human being on this earth have different fingerprints. Every single element is going to have a different spectrum. But my fingerprints will never change. Calcium's fingerprint will never change. Okay, so here's an example. This bottom spectrum is a spectrum from a star. So what elements are in the star? Let's use what we have. Okay, I see 2 lines. I see a line around purple and blue. Calcium doesn't have it. Sodium doesn't have it. Iron has it. Iron also has a line of green. Let's make sure our example has that. Let's follow that down. Yep, it's there. So we have iron. Now I have some other lines. That means I'm not quite done yet. I could have magnesium, but magnesium doesn't have these 2 other lines. Let's follow this up. I see a line here, calcium. And if I follow that red up, another line. Let's double check this one. That one matches. So this element or this star would have calcium and iron in it. Now we can use these spectroscopes to figure out not only the composition of a star or the ratio, I can also figure out what direction the star is moving and how fast. How cool is that? That's amazing. Okay, so we use what's called the Doppler effect. The Doppler effect demonstrates, you can hear this by sound wave or light. It does it with both in sound and light. But it's the apparent motion of an object. So it's what direction and speed is that object moving in relation to whoever's listening or seeing it. So we have 2 types of motions. We have something called blue shift and something called red shift. Blue shift means the object is moving towards you, and therefore all those wavelengths are getting squished together, and my light is going to shift towards the blue side of the rainbow because those wavelengths are shorter. Redshift means my object is moving away from my observer, so my wavelengths are getting stretched out, and that means my color is going to shift towards the red side of the spectrum. Now, it doesn't mean that red-shifted light is always red. It just means it moves towards the red side. Okay, so in this example, you've heard this if you've, if you're just standing on a street and you hear a car go by. If a car's stationary, let's say it's blaring its horn, no matter where I stand, I'm going to hear the exact same thing. But if I start moving my car forward, and remember, they're just laying on the horn, the sound waves in front of the car are going to get squished together. The sound waves behind it are going to get pulled apart. So it'll sound something like this. So you'll hear a different pitch. You hear a high pitch when it's coming towards you, and then once it passes, you hear the pitch drop.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Doppler effect. The apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant, distant future.
Okay, so another really cool thing that we can learn is that we can tell if something, like I said, moving towards you or away from you. So if this is a spectrum of an object at rest, say a star that's not moving in relation to us, and I look at an object here, notice how these two yellow lines were here and they moved towards the blue side. Remember, a color doesn't have to necessarily be blue or red, but it moved towards the blue side. That means our wavelength got squished smaller. So that means it's moving towards me. If I look down here, this wavelength got shifted towards the red. So my two yellow lines were here and I moved over here towards the red. That means it's red shifted. My wavelengths got stretched out and larger, and that means it's moving away from me. I can also determine how fast an object moves by how far they shift. It doesn't matter if I'm going towards or away if I'm looking at speed, but just you have to compare how much they move. If I take a look at these two, I could get a ruler out and measure, but they look to be about the same. So these two stars are moving in different directions, but at the same speed. But if my yellow lines were shifted over to here, then this red shift would be moving much faster than the blue shift. Or if I take these yellow lines and I move them this way, that's a pretty big shift, so that would be moving faster than the red one, or the red shifted one. Surface temperatures of stars are related to color. So blue stars are the hottest, typically like 30,000 to 40,000 degrees Celsius. Yellow stars are around 6,000, that's about the temperature of our sun. And red stars are the coolest, around 2,000 to 3,000 degrees Celsius. Magnitude is how bright a star is. Brightness can also be used, the term can be used luminosity. So you might see the term luminosity in replacement of magnitude. Brightness is going to depend on the temperature of a star, so typically the hotter the brighter. The size, typically the bigger the brighter. And the distance away from the Earth, the closer the brighter. Hot stars are typically brighter than cool stars, and closer stars are brighter than stars that are farther away, typically, not always. So we're going to have two different types of magnitude, different types of brightness. If the apparent is what we would see on Earth, so what it appears to be to the naked eye. So if I take a look at these two stars, A and B, size is related to how bright they are. So they're the same size, so they look the same brightness to me. However, if I look in outer space, star A is really farther away than star B. But star A is brighter so that they appear to be the same brightness on Earth. Absolute magnitude is what they actually produce. So if we take all the stars in the sky and we line them up equal distance from the Earth, we will be able to compare their absolute magnitude, what their actual brightness is. In the 1900s, Hertzsprung and Russell compared temperature of stars to the magnitude of their stars. And they came up with a graph called the HR diagram, short for Hertzsprung-Russell diagram. And what they noticed when they started plotting all these, supergiants, which are really large stars, are going to be in the upper right-hand corner. If we take a look at our scale down here, this is actually on the right-hand side, really cool stars. Remember, cool was red, so these are typically your red stars. And over on the left-hand side are going to be your really hot stars. You have your whites and your blue stars are going to be really hot. Your absolute magnitude, this looks counterintuitive, but the bright stars are at the top and the dim stars are at the bottom. So supergiants are cool stars, but very bright. Giants are going to be not as bright, but still have a decent amount of brightness, but they're still cool. Main sequence are known for having this diagonal pattern. So for a main sequence star, and only for a main sequence star, the brighter it is, the hotter it is. Or the dimmer it is, the cooler it is. And white dwarfs can be found in the lower left-hand corner. They are typically very dim, but very bright. So main sequence stars, again, they're on that diagonal line in the HR diagram. Our sun is a main sequence star, and our sun can be found in the middle of that HR diagram. So we're here, we're a yellow star. Red giants, those are large and cool, but bright. Supergiants are bigger and brighter than the red giants, and white dwarfs are small, very hot, yet dim.